So, Assalamu alaikum. So, let me go over the uh, basics of nearly free electrons. So, today I'm going to start the 16th lecture. Excuse me. So, lecture number 16 is going to deal with one of the cornerstones of condensed matter physics, and that is called Bloch theorem, which in one dimensions is also called Floquet's theorem. A quick recap of the different ideas that we've seen so far. When we have electrons inside a crystal and we ignore the periodic arrangement of the atoms, so we just have a free, non-interacting, independent sea of electrons, then these electrons are going to be modeled as plane waves. And a plane wave has a mathematical description. The mathematical description for a plane wave, as we all know, is Eik dot r. We would like to put a normalization constant with it as well. So this is our plane wave description of electrons. And this wave function is characterized by the wave number k, which we know is quantized. And we know that it's quantized because the volume of the solid material is finite, and imposing boundary conditions on the surfaces of this material, we arrive at the quantization condition. So if we just had a one-dimensional solid, for example, we know that the k value lies on a grid, and the k's are indexed by a number n 2 pi over a. So likewise, we have this quantization in 3 dimensions as well. So whatever the case is, we can characterize our wave function by this number k. So we put this k as a vector in a subscript. So this is the wave function for free electrons. And these wave functions are nothing but eigenstates of the Hamiltonian. The Hamiltonian is given by minus h bar square 2m over del square. And by the way, this potential, since this is constant, we assume this to be equal to 0. So the wave functions which I've written here, they are eigenstates of the Hamiltonian, and they solve the Schrodinger equation for free electrons. And the Schrodinger equation, of course, is given by these energies are the eigenstates. And we know very well that for free electrons, the dispersion relationship would simply be parabolic. And this m here, by the way, can be replaced by the effective mass m star, which was the topic of our discussion in the previous lecture. So if you were to plot this dispersion relationship for free electrons, I put k here on the x-axis, and this k represents the magnitude of the vector k, and I put the energy on the y-axis. And if I were to plot the dispersion relationship, this turns out to be a nice looking parabola. So far, so good. Now, these are free electrons which are also independent, which means they are non-interacting. They don't interact with one another. Now, if we were to start considering the periodic arrangement of the ionic cores from which those electrons come in the first place, then we modified this parabolic dispersion relationship. And we found out that even though the dispersion relationship looks more or less the same for most values of k, at critical points on k, the dispersion relationship is punctuated. So let me draw the new dispersion relationship for what are called nearly free electrons. Okay, so this is my K here, the energy. Let me also identify the critical points here. This is 0, pi over A, pi over A, 3 pi over A, minus pi over A. So for purposes of illustration, I'm using a one-dimensional concept of a solid, by the way. Okay, because we're going to talk about three-dimensional solids and three-dimensional Brillouin zones in a minute, but for the time being, we're focusing on 1D because it's easier to draw. So let me also draw these visual guides. For a nearly free electron case, the dispersion relationship is almost parabolic. However, it departs from parabolicity at the points pi a and minus pi over a. And these points, by the way, are separated by 2 pi over a, which is the length of a reciprocal lattice vector, G. In the next, across this critical point pi over a, had there been no periodic potential, you would start off at this point, but you really start off from somewhat later in the energy, higher energies, and you get curves of this kind. So there are certain punctures or discontinuities in this dispersion relationship, and those discontinuities occur at precise points, right? So if I were to label certain regions of K space, so the K point pi over A and minus pi over A, there is a gap of energies. No energy levels exist at these precise values of K. So in green, I'm representing the regions of zero energy levels. No K can exist. Sorry, no energy can exist in these green forbidden gaps, as they are called. Now, this is also related to the concept of bands, and I'm going to show that at the end of this lecture. What does this have to do with bands? But what we see here is that the dispersion relationship is punctured. There's a nice parabolic bowl-shaped curve, but at those critical points, which are the boundaries of the Brillouin zones, the dispersion relationship deviates, and we can find the size of these gaps. These gaps have a particular size, and that size is given by, we all know it's given by the time independent perturbation theory. It turns out to be 2 times Vg modulus. Likewise, this gap can be found out by time independent perturbation theory, and so on. And this was the content of lecture number 14. So in the nearly free electron case, we open up these gaps. These gaps are forbidden gaps, and no energy level exists inside these gaps. So the dispersion relationship resembles a plane wave in most points of K. However, certain K values at certain K values, the energy levels just disappear. You cannot have waves at those K values. And looking at this from the perspective of physical intuition, when a wave number approaches pi over A, the Bragg condition, which is given by 2 d in this case is A, sine theta is 1, this equals n lambda. When this condition is satisfied, and if I put this equal to 1, this would imply that K equals pi over A. At this precise point in K, the incident wave, which is traveling towards the right, say, will be reflected by the scattering planes towards the left, and the incident and the reflected waves, they will interfere with one another to form a standing wave. And that standing wave may have an energy lower than or greater than the unperturbed energy. So the standing wave could be of two kinds. You could have a plus sign between the left and the right propagating waves and a minus sign between the left and the right propagating waves. So this is the condition of Bragg reflection of these plane waves inside the atomic crystal. The atomic crystal is now acting like a grating or is diffracting electron waves. Bragg condition is a universal condition. It applies to X-rays being scattered off from electron densities, and it also applies to plane waves of electrons being scattered off by the atomic centers inside a solid. So this is a recap of what we've already covered. Now we would like to talk more about the Bloch theorem, and we would like to see what is meant by the Bloch theorem. But before I'm able to do that, I would just like to give a quick recap of Fourier transforms, because this is something really important. So if I have some function of space, I multiply this with a plane wave, I integrate over all of space. The new function that arises is the Fourier transform of small f, which I now represent by a capital F with the hat on top of it. Okay. Now there are different possible definitions and different normalizations, different pre-multiplying factors that go with the Fourier transform. We just have to be consistent. So likewise, I can also do the reverse. If I have my function of interest in the real space or the direct space, I can decompose this as plane waves, each plane wave of wave vector k being multiplied by capital F, which can also be treated as a coefficient with the plane wave, which is called the Fourier coefficient, which is determined from the first equation. And then I integrate over all of k. And then I normalize. And my normalization factor is the volume of each point in the k space. We know that in 3Ds, that volume is 2 pi whole cube divided by the total volume of the solid. So I have a solid of total volume V. This becomes V over 2 pi cube Tk Fk E minus Ik dot R. So we would like to keep in mind these definitions. So this is the decomposition of a function, be it periodic, be it aperiodic, into plane waves, each plane wave being modulated or multiplied by the Fourier coefficient, whereas the Fourier transform defined in equation 1 is as I've shown or highlighted in purple color. Now with this, equipped with this arsenal of Fourier transformation, we can start approaching the Bloch theorem. All right, let's move ahead. Before I go on to the Bloch theorem, I would like to talk a little bit about periodic functions. Functions that are periodic in the direct space. Now, of course, for a crystal, we have periodicity. After every lattice vector. So a lattice vector can be defined as, say, M1A plus M2B plus M3C, where A, B, and C are primitive lattice translation vectors. M1, M2, and M3 are integers, positive, negative, it doesn't matter. So now a periodic function is a function which repeats itself at every R. So you add some multiple of the unit translation vectors, you'll get the same function. An example is the potential function. The potential function, as you know, has to be periodic. That's how we've defined a crystal in the first place. That's how we've defined a lattice in the first place. Now, if I were to look at equation number 3, I can express any this function. Expression number 3 is valid for any function, be it periodic or aperiodic. So let's write this for the periodic function. So for the periodic function, I have V over 2 pi cube sum over all k. Look, you see, I'm just rewriting f. And now instead of the Fourier transform, I write rho k. Rho sub k, k means that I'm in the Fourier space. E raised to power minus I k dot r. So this has to be the same if I were to replace small r with small r plus capital R. It wouldn't make any difference whatsoever because rho is a periodic function. Now, if I were to do this, this is what I will achieve. Rho k, e minus I k small r, e raised to minus I k capital R. Now, if the function here is equal to the function here, what do I need to do? So I look at this function. R is any lattice vector, any lattice vector. But there is a finite number of lattice vectors in the solid. Suppose there are n unit cells. We're talking about primitive unit cells here. So if there are n unit cells, there will be n n lattice vectors. Each lattice vector is going to, you choose an origin, and each lattice vector is going to take you to another unit cell inside that crystal until you've exhausted all the unit cells and you've reconstructed the entire crystal. Okay. So keeping that in mind, what we could say is that this expression has to be valid for all r's. If this expression has to be valid for all r's, what I could do is I could take the sum over all r's and divide by the number of unit cells. I will get the same result, which means that the expression that I've written here, this thing, I can express this as the following. I can sum up over all r's and divide by the number of unit cells. It's going to give me exactly the same result. And by the way, this has to be equal to 1 if rho r and rho r plus capital R have to be equal. So in order to preserve translation symmetry, this has to be equal to 1. But now I'm doing a trick here. I'm replacing this exponential factor by this lattice sum. And why do I do that? Because of a result that I'm desiring, and this is going to reveal itself in a minute. So my rho r becomes v over 2 pi cube 1 over n g cube k rho k sum over all r's. Excuse me, just out something. So here I need this factor here. So here I go. I write this factor e minus I k dot with small r sum over capital R e minus I k capital R. This is my rho r. All right. So now from, does this term here, does this look any familiar? Yes. In lecture number 9, when we were looking at the Fourier transform of the lattice, we got the reciprocal lattice, we encountered these lattice sums. Remember from lecture number 9, we have something of this kind, say, so let's talk about 1D. In 1D, this is our connect. So I have x minus NA. And if I were to sum this over all n's, which means I'm looking at all lattice translation vectors, and I took the Fourier transform of this, I would get e raised to power minus I k n a summed over all n's. Okay, and we also notice that this must equal 2 pi over a sum of Dirac delta functions in the K space peaked at 2 pi over a. This is from lecture number 9. Okay, so you have to revise your notes to see if you remember all of this. So a sum of Dirac delta peaks has a Fourier transform, which is also a sum of Dirac delta peaks. In the real space, the spacing between the lattice points is a, and in the Fourier space, the spacing between the lattice points is 2 pi over a. That's how we've defined the reciprocal space. Now, exactly in the same vein, the same fashion, this lattice sum, which I've underlined in purple, E minus I, K dotted with R, is going to be equal to the 3D analog of this, which is 2 pi cube over the volume of the unit cell. So I represent this by small v. Capital V is the volume of the solid, and small v is the volume of the unit cell. And now I need a three-dimensional Dirac delta function in which k minus 2 pi over a becomes a reciprocal lattice vector. Excuse me. So G is now a reciprocal lattice vector. All right, so far so good. So this is equation number 4. This is equation number 5. So what this means is, now there's a difference between some students are confused between K and G. K, as you know, is quantized because of the finite size of the object, and G is a reciprocal lattice vector, which is some multiple of the length of the K point. So in 1D, for example, I will have K points that are spaced 2 pi over L apart, where L is the length of the solid. And I will have reciprocal lattice vectors of length 2 pi over small a. Okay. So there will be a large number of K points within the length of one reciprocal lattice vector. And if you want to find the number of those points could be easily found by dividing 2 pi over a with 2 pi over L. The answer is L over A, the length of the solid divided by the spacing between two lattice points. And this is going to be equal to the N, which is the number of points in the number of unit cells inside the solid. Okay, so we really have to keep this distinction in mind. So what equation number 5 is telling us, that the sum of these exponents is equal to Dirac delta peaks located in the K space at the reciprocal lattice points, at the G's. Now I could put this expansion of the lattice sum into equation number 4. Okay, and let's see what I get then. Rho r becomes equal to v by q 1 over n. Here I have d cube k rho k e minus I k dotted with r, sum of r. So this becomes sum of k's, by the way. So I get two. I need to take into account this term 2 pi cube over small v k minus g. And by the way, sorry, one mistake that I made. This is a sum over g's here. Sorry, sum over g's. I'm sorry, I made this mistake here. So this is sum over g's. I have to take all the g points So remember, my k is a constant here because I'm taking a sum over lattice points. So my answer must have a k, must have a k as a variable. So I'm taking the sum over g's in equation number 5. So I have sum over g's, and I'm also have an integral with respect to k. This is what I get. So this is something that is easy to see. I can, first of all, let's get rid of these terms. This goes away. N small v is simply capital V. The number of unit cells is capital. Multiplied with the volume of each unit cell gives us the total volume. And now, if you observe, I just write down this sum over g's. If you look at this integral, I can employ the sampling theorem. The sampling theorem means that I have some function being multiplied by a Dirac delta function in the same variable, which is k. So I'm really sampling those values of k which are equal to g. So I need to find out those points in the function rho ke minus k dot r when k hits a value of g. So I'm taking out or sampling those values of k. So, so when I do that, this integral goes away, and I'm left with rho sub g e minus I g dot with r. All right, so this is what I desired to describe. Any periodic function in the real space can be written as a sum of Fourier coefficients sampled at values of g and multiplied by the plane waves in which the phase is g dot r. And since I'm summing over all g's, I can either put a plus sign or a minus sign here. It doesn't really matter because my g's go from some positive to some negative number. So the origin is 0, and they are symmetrically extending into both positive and negative regions. So any periodic function whatsoever can be decomposed in this fashion. If I were to talk about a periodic potential function, write this as sub g e plus minus I g dot r. And I can immediately see that this is periodic. So if I were to take this expression here, number 6, add capital R to it, see, let's see what do I get. Sum over g's, rho g e, let's choose the minus sign, g dotted with small r, e minus I g dotted with capital R. Now look at this term over here. A fixed reciprocal lattice vector and a fixed direct lattice vector, I take the dot product, and we know from the definition of the reciprocal lattice vectors that this dot product is some multiple of 2 pi, because G we know is some H A star plus A B star plus L C star, and R we've already mentioned is M1A plus M2B plus M3C. If I take the dot product, this turns out to be 2 pi into some integer. Hence, this term is nothing but equal to 1. So all of this turns out to be equal to rho r. So rho r is indeed periodic. Any periodic function can be written in this fashion. All right, so let's take a half a minute break. Now let's move to the gist of this lecture. The gist of this lecture is Bloch's theorem. Bloch's theorem, by the way, is one of the linchpins of condensed matter theory. Really important. We know that most crystalline solids, they are periodic. So it describes waves inside a periodic crystal. If now the Bloch's theorem comes in different disguises, it comes in different forms, and we're going to enumerate all of those forms today. So, what is the main idea behind the Bloch's theorem? The main idea is that if I look at the Schrodinger equation, this is my Hamiltonian, where this is a periodic function, which means Vr can be represented as Vg E minus I g dotted with R summed over all g's. This is a periodic function. I need to find out some eigenstates of this Hamiltonian, which also correspond to some energy. So the Bloch's theorem really tells us what kind of eigenstates exist for a periodic potential. We know that for a constant potential, the eigenstates are plane waves. But what are the eigenstates for a periodic potential? So Bloch's theorem answers this question. So if you were to pose a question, what are the eigenstates for a periodic potential? Of course, this is a kinetic energy term, and this is a potential energy term. The potential energy is periodic. You add a periodic potential to a kinetic energy term. What are the eigenstates? In other words, what do the waves look like for electrons inside a periodic potential? Are they plane waves, slightly modified plane waves, modulated plane waves? Bloch's theorem provides an answer to this question. And why is it important? We'll learn about it in a minute. So we would like to find out the eigenstates for this periodic potential. All right. So there are different forms of Bloch theorems. Let's look at the first form. Form number one. Form number one states that the eigenstates psi k r, they are given by plane waves. However, those plane waves are now being multiplied or modulated by another function. Let's call that function u. So, of course, a function of the real space and characterized by the index k. So, any solution to the periodic potential problem is called a Bloch function. So, this is form number one. The wave function is given by a plane wave modulated by another function uk, which has a special property that it shapes the periodicity of the periodicity of the potential. And the periodicity of the potential is through r. It's translationally periodic. So uk r plus r equals ukr. This is the first form of the Bloch theorem. Okay. Now we learn later that the wave function, therefore, if you look at this expression here, the wave function can be characterized by the wave number k. Okay, k gives you a plane wave, and k also determines the form of this periodic function u. So I can describe a Bloch function in ket space, or in quantum notation, I can write it as being identified by k. Later, we learn that there is another index, n, which is called the band index, which completely defines a solution to the periodic potential problem. We'll talk about this band index in a minute, but let's first focus on the first form of the Bloch theorem. The Bloch theorem states that the eigenstates of a periodic potential are plane waves modulated or multiplied by another function which shares the periodicity or has the congruent periodicity, the same periodicity as that of the potential itself. This is form number one for Bloch's theorem. And of course, we're going to prove it. So let's be patient. Form number two. Form number two of the Bloch theorem states that a function which is a solution to the Schrodinger equation with the periodic potential, that function is psi k. If I were to find out the function at some point displaced from R by a unit translation vector, or not necessarily unit, by some translation vector, then this is equal to the wave function at the point small r multiplied by a phase factor, which is given by Eik dotted with capital R. All right. So translation in the real space, this is translation, nothing but translation, results in a multiplication by a phase factor in the K space. So if I knew the wave function at some point small r, and I would like to find out the wave function at small r plus capital R, the wave function here is going to be equal to the wave function here multiplied by this phase factor Eik dot capital R, where R is the distance between, or the displacement vector between the 2 points. This is form number two. I can yet write another form. Form number three. Form number three is the following. Since U is periodic, I can express U in the following form. U, K, some function of G. So I don't want to write so many subscripts. So instead of writing G in a subscript, I now write it as an argument. Sum over G's, E minus I G dotted with R. This is simply what I do for any periodic function. You see? For any periodic function, I have this thing or this thing. So form number three means that I can write psi k function of R. This is form number one. E I k dotted with R U K R. This is form number one. So now, since this is periodic, I can put this expansion of UK into form number one, resulting in Eik dotted with small r sum over G's UK G E minus IG dotted with R, which will result in sum over G UKG E minus E plus I K minus G dotted with R. This is form number three of the Bloch theorem. The Bloch's theorem comes in different guises, comes in different garbs, and these are the three forms of the Bloch theorem which are most important and which are most commonly used. So now we would like to prove the Bloch's theorem. So let me do a quick recap. Number one, the Bloch function, which is an eigenstate of the periodic Hamiltonian, is a modulated plane wave. A plane wave is being multiplied by a periodic function. The periodicity of that function, which we label as u, is the same as the periodicity of the potential. Form number two, I take 2 points in space which are some translation vector apart, symmetric translation vector apart. The wave function at one point is equal to the wave function at the other point multiplied by a phase factor. That phase factor is given by the phase itself is given by k times the translation vector k dot r. That's form number two. And form number three is given as I've shown over here. Plane waves, the wave, the Bloch function is, this is a plane wave. Plane wave multiplied with a periodic function in at particular values of g, and you sum up over all g's. These are the three forms of the Bloch theorem. Now we would like to prove all of this. Okay. So like to prove of Bloch's theorem. We would like to prove this in one dimensions. So just for ease of understanding. All right, so if I'm going to look for an eigenstate of the Schrodinger equation with a periodic potential, what properties must that solution have? So that's the basic question. So that's our starting condition. What conditions must that solution follow? The solution must follow the condition that if I look at the wave function, I'm talking in one dimension, so I'll use the variable x. If I look at the wave function at some point x, and I look at the wave function at another point, which is distance a from the point x, since the periodicity is in units of a, a, 2a, 3a, minus 2a, minus 3a, and so on, the wave function at these translationally symmetric points, points that are related by translational symmetry operation, the wave functions must be such that if I were to take the modulus square, which represent probabilities for the occurrence of the electron, the modulus square must be equal to 0. So why modulus square? It comes out because of the Born interpretation of the wave function. The modulus square has to be equal, which means that the probability of finding the electron at x and at x plus a, or x plus 2a, minus 2a, plus 3a, minus 3a, the probability densities have to be the same. The wave functions can be different, but the probability densities have to be the same. This is because the crystal itself is translationally symmetric. There's periodicity. So what this means is that psi x plus a must be equal to psi x with some phase factor, because only then would the modulus square be equal to 0. So this is point number one. Point number two is we will apply the Born-Kármán periodicity constraints. Oh, Born. So this is not Kamran. It's Kármán. So we apply these periodic boundary conditions, which means that if I suppose I have a solid, one-dimensional solid, the wave function at x equals 0 must be the same as the wave function at x equals L, where L is the length of the solid. This is called a periodic boundary condition. So in this periodic boundary condition, psi x plus L must really be the same as psi x. Now, we don't have a modulus square. The wave function itself must be the same, because from all practical purposes, this point A is the same as this point B. There is no uniqueness in either of these points. Both of these points must be exactly the same. So their wave functions must exactly be the same. Okay, so these are called periodic boundary conditions. Now, if I look at uh, these periodic boundary conditions, what this means is that, by the way, if I look at expression number 1, this is expression number 2. If I were to take psi x plus 2a, then this must equal ei phi psi x plus a. But this must equal ei phi squared psi x, or ei 2 phi psi x. This means that psi at x plus L, which is really capital N into small a, L is the length of the solid, and this must equal capital N, the number of unit cells, the spacing of each unit cell. This must equal E I N phi psi x. But this must equal psi x from equation number 2. All right. So what does this mean? This really means that my ei n phi must be equal to 1. This means that my n phi must be equal to some multiple of 2 pi, which means that my phi must equal m 2 pi over n. This means from equation number 1, which I've written over here, this thing. Now I know what my phi is going to be. My phi is constrained. I cannot have an arbitrary value of phi. So if my phi is constrained to be of this kind. Okay. Now, if I were to use this expression for phi inside equation number 1, my psi x plus a, this is equation number 1 written again, equals ei phi, which is now 2 pi small m over capital N psi x, where this m is, could be 0, could be plus minus 1, could be plus minus 2, and so on. So let's call this equation number 3. Excuse me, equation number 3. And I can also write this as x plus small n a by 2 pi m over n times small n psi x. This must equal ei 2 pi mn, which is another integer. I can call this integer something else, small p. This is equation number 4. Let me put equation number 3 and equation number 4 inside a box. Now, any wave function, Bloch function, which is a solution of the periodic condition, must satisfy equation number 3. It must satisfy equation number 4. All right. So let's focus our attention on equation number 3 here. The Bloch's theorem proposes a solution to the Schrodinger equation with periodic conditions. Let's look at that solution. Let's look at expression number 1 for the Bloch theorem. Expression number 1 states, that psi kx given by eikx ukx in 1D. This is in 1D. Now we would like to ask the question, does this proposed function, Block function, satisfy the Bloch condition in 3? This is our question. If it does, we've proven that this is indeed a solution to the Schrodinger equation. It respects the periodicity condition. It respects the Bloch condition number 3. Okay. So let's see if this is true. If I were to look at the Bloch condition, let me rewrite the Bloch condition. X plus A is EI 2 pi m over n psi kx. Now my proposed Bloch function is given over here. So I look at the left hand side, psi kx plus A is given by EI kx plus A u kx plus A. This is my left hand side. Now this is EIKA, EIKX. This object is periodic, so it becomes equal to UKX. This is equal to EKI times the original. Okay, so this is my left hand side. The right hand side, if I were to plug the right hand side of my proposed solution into the Bloch condition, EI 2 pi m over n psi kx, psi kx is EIKX UKX. So this becomes excuse me. So the left hand side, all of this is psi kx. So the left hand side equals the right hand side if Ka equals 2 pi m over n. Or K equals 2 pi m over n small a. But what is n over small a? It's L, 2 pi over L m. So what this means is that our proposed solution, which was proposed by the Block theorem, indeed satisfies the Bloch condition, which is equation number 3, provided K equals these values, 2 pi over L into M. And that is indeed what are the allowed values of K. K, as we've already noticed here, so if you go above, the allowed values of K are, I've drawn a 1D, this, look here. These are the allowed values of K. So if I put K equals 0 here, this point is 2 pi over L, this point is 2 times 2 pi over L, this point is 3 times 2 pi over L, this point is minus 2 pi over L, and so on. So K is indeed quantized in units of 2 pi over L. Hence my proposed Bloch function, which was the first form of the Bloch theorem, which is a plane wave being multiplied by a periodic function, is indeed a solution for the Schrodinger equation because it satisfies the constraint imposed by the non-uniqueness of the wave function. The wave function has to, the modulus square has to be equal. After every A, the modulus square or the probability density of the wave function has to be the same. After all, it's a periodic crystal. Hence, we've proven the first form of the Bloch theorem, provided this is true. And this is always true because this is how we've defined the K points. The K points are punctuated points. They are discrete points which are separated out in the reciprocal space by units of 2 pi over L. 2 pi over A in the x-axis, 2 pi over B in the b-axis, and 2 pi over C in the z-axis. Okay, so you have a grid of points inside the K space. And the wave functions, let me rewrite the wave function, which is an eigenstate of the Schrodinger equation. The wave functions are plane waves, eikx, multiplied by ukx. And in 3D psi k, the function of r becomes eik dotted with r ukr, where this is periodic. Okay, provided k is of the right kind, the k is properly quantized. So you have plane waves in which the k's are reciprocal points in the reciprocal space, k space, and these are not, by the way, reciprocal lattice points. These are points in the k space, and you take those values of k, form plane waves, and multiply those plane waves with a periodic function, some periodic function which has the periodicity of uk. Now this uk is not general, it has to be a particular solution. And I give you a homework problem so that you can find out what other constraints must this periodic function satisfy. Okay, so this is proof of version number 1. So if I look at version number 2, I know, let's start looking at form number 1 again. If in this form I replace x by x plus a, let me see if I recover form number 2. So I just replace x with x plus a, eik, this right hand side x becomes eik a to eik x psi k x plus a. This becomes ik eik x eik a, and this is ika into the original. And this is nothing but the second form of Bloch's theorem. Which tells us that the wave function at some point displaced by a lattice vector is the original wave function, and it accrues a certain phase factor, picks up a certain phase factor. Sorry, by the way, excuse me. By the way, this thing here is psi kx. All right. All right. So one